This is Advanced Math, Unit 12, Lesson 5. What you should have out right now is, of course, your notes, a scientific calculator, and your Unit 12 packet. Okay. Change up base, excuse me, theorem, and half-life problems. Solve. Number 1. Log base 5 of 30 equals x. Okay, so we have our calculators are not programmed, well, at least these type of calculators are not programmed with a base of 5 or any other base other than a base of 10, that's the log key, and a base of e, which is your ln key, your natural log. Okay, so we cannot just plug this in the calculator the way it is. So we're going to use our tools to be able to solve for x. Okay, we know that if I were to write this in exponential form, it would be 5 raised to the x equals 30. We've did 5 to what power is 30. I can't raise both sides to the reciprocal because my power is the variable that I'm looking for. One of the log laws that we reviewed in an earlier previous lesson was an exponential. So if I have a log on both sides, or if I take the log of both sides, I can bring the exponent down. Okay. Now, since I can take any log, I could take log base 10, I could take log base 12. I'm going to do log base 10 only because that's what I have in my calculator. I'm going to scoot this over just a smidge. Okay, so I'm going to take log of both sides. Now, I'm not multiplying by log, I'm taking the log. It's like taking the square root of both sides. Again, I'm not multiplying by log, I'm taking the log of both sides. So I'm taking log of 5x and log of 30. Okay, we learned, or you learned in previous years, but we reviewed in a previous lesson that when you have a log with an exponent, you can kick it to the front. That was log law number 3 from lesson 12.3 right there. That's what we're going to do right now. So we're taking the k, or the x in this case, to the front. X times log of 5 equals log of 30. Now these both have a base of 10 because it's not written, and that's the way we set it up. We want to solve for x, so we divide both sides by log of 5. Remember, log of 5 is just a decimal in your calculator waiting to come out. So that here is what you're going to plug in your calculator. Now, what you can and cannot do, when you type it in, you're going to type in log 30, close parentheses, divide log 5. Do not, kids often say, well, can I reduce the 30 and the 5? You cannot. If it was like this, do you see the difference between these two? Log 30 over log 5 versus log of 30 over 5. This has two separate logs. This is log of a fraction. This is a fraction with two logs. These are two completely different things. This one here does equal log of 6. That one is okay. This one here does not equal log of 6. Cannot reduce. You just have to plug it in your calculator separately. Okay, so log of 30 divided by log of 5. Log 30, you can't see it that well, but you hopefully figure it out. Log of 30, close parentheses, divide by log of 5. So there it is there, log of 30 divided by log of 5 equals, and there's our decimal, and we're going to round to 3 decimal places, the thousandths, 2.113. Okay, number 2. Log base 12 of 7 equals x. And after number 2, we will talk about the change of base theorem and how we can use that. Okay, so do the same thing we did before. Recognize that we do not have a base 12 in our calculator, so we're going to rewrite it. 12 raised to the x equals 7, wrap around. Take the log of both sides. Why are we taking the log of both sides? So that I can get the exponent to the front. And the whole reason we do this is for what I just said. We want to kick this exponent to the front as a coefficient. So x times log of 12 equals log of 7. And we want to solve for x, so we divide both sides by log of 12. Gone. X equals, and then you just plug that in your calculator. Go ahead and do that now. I'm going to type it in, and then I'll pick it up so you can see it. Log of 7, close parentheses, divide log of 12, close parentheses. That last one you don't have to close. Let's see if it gets in there. Gosh darn it. Okay. And then you hit equals and 3 decimal places, 0.783. 0.783. All right. So this way works. It'll always work. You can always do it this way if you ever forget the change of base theorem. Now here is how the change of base theorem works. Let's write this down. Change of base theorem. If you have log base b of a and you cannot plug it in your calculator, even if you could, it doesn't matter, but let's pretend this is something we cannot plug in our calculator. Let's look at here. Log base b of a. B is 5, a is 30. When I went to plug it in my calculator, where is it? It's right here. I did log of 30 divided by log of 5. Let's see if that's the same thing we did over here. Log of 7 divided by log of 12. So it looks like it's going to be log of a divided by log of b. Okay, so log of the larger in size, not value, the larger in size number divided by log of the base. Log of a over log of b. Okay, so, and you can use this from now on. Now, if you forget this, I'm like, what was it? Log of what over what? And you just can't remember. Do it this way. This way will always work. All right, so how will we use this from now on? Evaluate using the change of base theorem. Log base 3 of 17. Okay, do you see how there is no x? Now, if you wanted to, if it didn't say this up here and it just said evaluate, if you wanted to, you could rewrite it as 3 to the x equals 17. And I didn't address that over here, and I'm going to quickly. I'm going to cover the log and cover the log. 5 to the x equals 30. We typically try to get those to the same base, but we can get 30 to a base of 5, which is why we took the log of both sides. Same thing here. 12 to the x equals 7. We can't get those to the same base, which is why we did log of both sides. Now, if you rewrote this as 3 to the x equals 17, same thing, you can't get them to the same base. So we're going to use the change of base theorem, which is log of the larger in size, 17, divided by log of the base, log of 3. And that there is what you're going to plug in your calculator. Go ahead and do that now. Log of 17, close parentheses, divided by log of 3. You can see I didn't close the last one on this one, if I can ever get it in. And that is okay if you don't. I don't know why it's acting funny. Equals 3 decimal places, 2.579. Number 4, log base 6 of 0.1 equals log of 0.1 divided by log of 6, and plug it in your calculator. And 3 decimal places should give you negative 1.285. Log of 0.1 divided by log of 6 equals, and there's your decimal. It does come out to be a negative number, and that's okay. Negative, what was it, 1.285. All right. I'm going to go back to solving. Solve number 1. 8 to the x equals 214. You have choices on this one. You can rewrite it in logarithmic form. Log base 8 of 214 equals x, and then use the change of base. Or use the tool that we did up here with take log of both sides. You do want to know that tool because it's something we're going to use when we come to solving word problems. Take log of both sides. And even then, you can still rewrite in logarithmic form. But I'm going to get the practice with taking log of both sides. If you'd like, you can try doing rewriting it in logarithmic form. It would be log base 8 of 214 equals x. 8 to the x equals 214. And use your change of base. I'm going to continue, bring x to the front, log of 8, and then divide both sides by log of 8. This is what you're going to plug in your calculator. X equals log of 214. And take a step back. Remember, we're doing this because we can't get these to the same base. That's the whole reason we're doing it this way. Divide by log of, and I forgot to write the log, sorry guys, log of 8. All right, so plug it in, log of 8 equals 2.580. Log of 214 divided by log 8, 3 decimal places, what was it, 2.580. Okay, number 2, e raised to the 2x equals 12. We're going to do the same thing. We're going to take log of both sides, but this time, because it's e here, I'm going to take log base e of both sides. I'm going to write it that way. Log base e of e to the 2x equals log base e of 12. And I'm going to change it in the next step because log base e, we typically never write it as log base e. We just write it as ln. ln of e to the 2x equals ln of 12. Log base e is the same as ln. Log base e, ln. Okay, the 2x gets kicked to the front. So we have 2x equals ln, oh, sorry, no equals yet. 2x ln of e equals ln of 12. Now, you can divide both sides by ln of e. You can, but I'm hoping you recognize that ln of e actually equals 1. If you think about it, I'll put a little note here. Ln of e is equivalent to log base e of e. And if you were to set that equal to x, e to what power equals e, x is 1. E to what power is e? 1. So ln of e is always going to be 1. All right, so that leaves behind 2x equals ln of 12, divide both sides by 2. X equals, plug in your calculator, you're using your ln key now, ln 12 close parentheses, divide by 2, 1.242. ln of 12 divided by 2, 1.242. All right. Okay, next thing we're going to do is one of our homework problems. That's why I asked you to have your packet out. Homework problem number 14. This is from, what lesson is this? Lesson 5, so this is from worksheet 5. So open up your packets to worksheet 5. And we are going to do number 14. Find the half-life of strontium-90 if K equals 0.0246, where A equals A naught times e to the negative KT, and T is expressed in years. All right. I'm not going to write everything down, but I'm going to write down information that we need. Okay, find the half-life of, actually, I'll just get it down. Find the half-life of if K equals 0.246 and A equals A naught times e to the negative KT, and T is expressed in years. Okay. What we're looking for here is the half-life. Well, that means we're looking for the amount of time, which means T is what we're looking for. We're looking for the amount of time it takes for this element to reduce to half of what we started with. So if we started with 50, we're looking for the amount of time it takes to end up with 25. If we started with 100, we're looking for the amount of time it takes to end up with 50. Whatever it is we're dealing with, the amount of time it takes to end up with half of what we started with. All right, so things you should know. A is the amount after a given time. A naught is always going to be your initial amount. K is your constant. And T is the time. Okay, so we're looking for the amount of time it takes for us to end up with half of what we started with. Now, unfortunately, it did not tell us what we started with. Do you recognize that in the problem? It didn't tell us, hey, if you have this, and over time you have this. If they ever do that, you just make your initial amount 1. Technically, you can make it any number you'd like, but I'm just going to pick 1. If my initial amount is 1, my amount after given time is going to be half, and time is what I'm looking for. Okay? So we're going to look for the amount of time it takes for us to end up with half of what we started with. If you wanted to, you could have put 10 here and 5 there, or 12 here and 6 there. It does not matter. I'm just always going to use 1 and a half. 1 for the initial, half for the amount after given time. Okay, plugging in. 1/2 equals, A naught is 1, E is just a number in your calculator, K they gave us, negative 0.246, T is what we're actually looking for. Okay, so here's my equation. 1/2 equals 1 times e raised to the negative 0.246 t. All right, first thing I'm going to do is get rid of that 1. We don't need it there. So 1/2 equals e raised to the negative 0.246 t. And we just did some of these solvings on the previous problems, actually right up here. I'm going to take ln of both sides. Now, if you wanted to, you could rewrite in logarithmic form. I'm just going to do ln of both sides. So ln of 1/2 equals ln of e to the negative 0.246 t. Now, how do I know when to take the log or the ln of both sides? It's when your variable is in your exponent. Your exponent has your variable. Like it happened here. Here's my exponent, and it's a variable. I took log of both sides. Same thing over here. here's my variable, it's an exponent, I took log of both sides, and we kept doing that even down here. There's my variable, it's an exponent, I took log of both sides, and I do that to get the variable down to the coefficient. Okay, so we're going to do that next. This is going to get kicked out to the front. So ln of 1/2 equals negative 0.246t times the ln of e. And we did talk about ln of e earlier. It is 1. And I explained it earlier on why. So I have ln of 1/2 equals negative 0.246 t. I'm solving for t, so I'm going to divide by that decimal. Negative 0.246, negative 0.246. T equals, and just plug it in your calculator, ln, I'm going to use 0.5, 0.5 close parentheses, divide by negative sign 0.246. And I apologize. Oh, okay. Wrote it wrong. All our work is correct. Nothing's going to change in any of this. It's just when I read it versus when I wrote it, I wrote it wrong. This piece right here. And I'm sure you guys caught that already because you had your packet in front of you. 0.0246. And that just means here there's a 0, a 0, a 0, and a 0. So plug it in again with that 0 there. Zero, 2, 4, 6. All right, plug it in one more time. ln 0.5 close parentheses divide by negative sign 0.0246 equals 28.177. 28.177 years. And that is it for this lesson.